Hello, class. I realized on that last video that I had to switch this from the extra wide screen to the more narrow screen for a Zoom meeting that I had with the faculty the other day. And I forgot to switch it back to the 16 by 5. Anyway, what I've done is you're going to see that this second one is actually wider. You can actually see it's closer. It also means that I put a little black line down here so I know I cannot write below that line. Of course, that line's just about the end. And I've tried to fashion my studio here at home so that we can get as much in there. Now, where were we up to at the last time that we were talking about dimensions? We got through all the primary dimensions. And what we wanted to do now, yeah, I sort of screwed up there. I'm just going to make that thicker. So what we want to do now, let's just go back to the ones that we were at. So area, and we know the area, the defining equation for area is, let's say, length times width. You know, we can do a whole variety of things, but we know that area is now going to be meters squared. We know that volume is meters cubed. And I'll leave that for last lecture. You can take that off the last lecture, what the defining equations are for volume. Velocity, and again, I went through a very detailed explanation of velocity and also differential operators and how those work. And we know that that is meters per second. And we know acceleration. And again, you know, all of these, that would be meters per second squared. We got up to force. And we saw that force was equal to mass times acceleration. This was the first one where we actually used what we had derived in our earlier dimensions, the units that we had derived in our earlier dimensions from using equations that exclusively used the primary units. And that gave us all of these. Now we're using these that we've derived already, sort of like a mathematical proof, isn't it? Into this. So force equals mass times acceleration. And we know that mass is going to be a kilogram. And we know that acceleration is a meter per second squared. So we know that it's going to be kilogram meters per second squared. That's how we as engineers view force. We don't view force as some nickname that somebody gave to that so that people could just put a two-syllable nickname rather than understanding it at the base level. I wonder if the whole nation, well, come on, they're not going to do Yes. At least there's a higher emphasis nowadays on, you know, technical literacy. And it had been going the other way for a very, very long time. You know, our country was really built on technical literacy. In fact, at all of the major service academies, West Point, Annapolis, out in Colorado Springs, I think that's where the Air Force one is. All of those, everybody that graduated from the service academy was an engineer. I think that was the same way up until around the year 2000, or maybe Bill Clinton changed it a little bit earlier than that. I can't remember. But, you know, I've always thought an engineering education, that's a good start. Let's go to the next one. So we've got force. Now we know that energy equals a whole lot of things, but we know it equals force times distance. Now, why am I choosing force times distance? Well, we already have derived force right here, haven't we? And we know we've got distance. Now, could we use something else? How about this? Isn't it mass times velocity squared over 2? Couldn't I use that to figure out what my primary units are? Because we've already also derived velocity, haven't we? And we've got mass as a primary unit. How about if I said that it was mass times the gravitational constant? Of course, the gravitational constant, you know, we should put that here probably. You know, because that's a subset of acceleration, isn't it? So we know that G, the gravitational constant at the surface of the Earth, and this is an average, it's actually slightly different at the poles than it is at the equator, is going to be 9.81 meters per second squared. And I think everybody knows that and has committed that to memory, gotten that. But if we have mass times the gravitational attraction times the height above ground, we then have, or whatever your reference plane is, we then have potential energy. So we've got force energy, kinetic energy, potential energy. I could go on and on and on and on and on, couldn't I? But the truth is, it's just force times distance. So let's use that one. So we've got a kilogram meter per second squared times a meter. So what's that going to give us? That's right. I think everybody sees it's a kilogram meter squared per second squared. We have a nickname for that. And I think everybody knows that it's called a joule. Right? So that's how energy and force and acceleration, velocity, volume, area, how they're all interlinked with one another, aren't they? And we can see that again. We think in terms of kilogram meters per second squared for force, and we think in terms of kilogram meters squared per second squared for energy. That's what sort of separates the way that we look at these various dimensions. And of course, it allows us to use these dimensions. Knowledge is power. Remember that. And you've got to, of course, use your power, your supernatural power, which is your brain, to overcome all this. All right, now we've got energy. How about power? Power is related to energy, isn't it? You know, let's say that I had a power plant. I've got a power plant, and this power plant that I've got, it makes, I'm just drawing a power plant here. Oh, there's a little chimney on the power plant. Oh boy, I am not very good. Thank God I went into engineering and not into power plant design. Oh wait, you can't see through that. It's a glass chimney. All right, so I've got this, and it's got 3 gigajoules. Does everybody know what I mean by giga? Does everybody know what I mean by giga? Hey, let's do that. Why don't we start here? Why don't we start at 10 to the 3? What's 10 to the 3? I think everybody knows that's right? Kilometer. 10 to the 6, mega. 10 to the 9, giga. And of course, that would be a million and a billion. And then we've got 10 to the 12. Right? What is 10 to the 12? It's not a billion, it's a trillion. That's right. And so we call that tera. And get these down so that you can refer to them. In fact, as you go through the electrical engineering program, you're going to be dealing with pico farad capacitors, right? Picofarad. What is pico? Is that 10 to the 9, 10 to the 12, 10 to the minus 9, 10 to the minus 12, 10 to the minus 15? What? So you have to memorize these if you haven't already. And I find that students that get to this point still haven't memorized all of their prefixes. Also, I want you to immediately change your calculator, right? If you're going to be engineers, you're going to change your calculator to engineering mode. That's right. You can choose engineering mode or you can choose scientific mode. Leave scientific mode behind. I don't ever want to see any answer on any test or any homework that I give you that is not in multiples of the integer of 3, right? You can see that engineers use thousands to separate out what they do. They know these by heart. I know these by heart, right? I know, you may not, but 10 to the 15 is peta, right? 10 to the 18, exa. So you should know all of those. You should really commit to memory all of those that I've talked about so far. And then 10 to the minus 3, a lot of people have that. Milli, right? Millimeter. 10 to the minus 6, micro. You know, I'll write micro, but then we use the Greek mu to specify micro usually. Whereas we use M to specify milliseconds, right? We use K to specify things like kilohertz, you know, everything like that. M for mega, G for giga. As a matter of fact, didn't I use that? Oh yeah, 3 gigajoules. See how the J is joules and the G is giga? And then T for tera, P for peta, E for exa, so on and so forth. Let's go to micro now. Now we've got 10 to the minus 9. 10 to the minus 9 is nano. And we use a small n for nano. 10 to the minus 12. Pico. And we use a small p for pico. 10 to the minus 15. Now, you're probably saying, when am I ever going to get down to 10 to the minus 15? I mean, pico is already small enough. Nano, I mean, a nanometer is already small enough. Pico, what am I talking about? Picometer, wouldn't that be like the size of the nucleus of an atom? No, actually, we get down to about 10 to the, anyway. So 10 to the minus 15, I'll tell you what, femtosecond laser bursts. That's right. Femtosecond laser bursts are where we are at now with pulse mode lasers, right? So, in fact, we're even lower than that. We are almost to 10 to the minus 18, right? Atto. So these over here are the prefixes. Now, you're probably saying, isn't there a 10 to the 21? And isn't there a 10 to the minus 21? Minus 21, I think, is Yato. And 10 to the 21, I can't think. You know, there's even one that's below. Anyway, I think you're fine with these. I think if you memorize these, you should be good. And no engineer will spite you for not knowing that 10 to the minus 21 is Yato. All right. Now, let's get back to the derived units. And I want to get back to this. Let's say that I give you, here's a power plant, 3 gigajoule power plant. How much will you give you for that? A 3 gigajoule power plant is worth $10. Because what is that 3 gigajoule power plant? Well, that's the little generator that I have on my front wheel of my bike that powers the little light that's on my bike, right? That generator, that's the power plant I'm selling you. That's a 3 gigajoule power plant. How do I know that? Because I could run that. I could sit on my bike and I could just, for 70 years, keep pedaling that. And in 70 years, maybe it wouldn't even take me 70 years, I could probably get 3 gigajoules out of that. Actually, it'd probably be a lot longer than 70 years. But yeah, What does that really tell us, right? That's not telling us what power is. It's a power plant. Power is the key word there, isn't it? Power plant. You know, power is energy divided by time. Energy divided by time. But we know what energy is already. We know that energy is a kilogram meters squared per second squared. And now we're going to divide that again by a second. You know, knowing that this will kill everybody on the plane if you get it wrong. What is that? Is that a kilogram meters squared per second squared? Or is that a kilogram meters squared per second? Or is that a kilogram meters squared per seconds cubed? If you get it wrong, everybody dies. Well, let's just do what we did in third grade. Isn't it really the numerator, kilogram meters squared over second squared, times the reciprocal of the denominator? You know, the denominator is really s over 1, isn't it? So this would really be 1 over s. That's right. Everybody that said it was a kilogram meters squared per second just killed everybody on that plane that they were designing. See what happens when you make mistakes and you're an engineer? People can die. Now, when you get things right, people can die too. I mean, if that's what your aim is and you're working for Raytheon or from one of the defense or military contractors, and that's what you're doing, you know, that is the defense of America. And of course, that has a purpose as well. However, I'm talking about accidental deaths and stopping those by using correct units and understanding how the variables and dimensional homogeneity go together. So that's right. What we really have is a kilogram meters squared per seconds cubed. And we have a nickname for that. It was named after James Watt. Yep. But again, that's not how we think of it. We think of it as a kilogram meters squared per seconds cubed, don't we? We can use that later when we start to do dimensional analysis and similitude and using that in our professional careers. All right, so we've got power. Now, one thing that I want to sort of look at now is the power equations. And I admit that you may have been introduced to these in your introductory class, but the power equation is for electrical engineering, the power equation is really just P equals current times voltage. P equals current times voltage. That's the only power equation. We really have two important equations, though. We've got the power equation, but then we also have a relationship between current, voltage, and resistance called Ohm's law. And I'm pretty sure that all of the people that have got here at least have heard of Ohm's law prior to this, or you might not have gone in to electrical engineering. But Ohm's law says that the voltage is equal to the current times the resistance, right? So using those two independent equations that we have, we can put together other equations for power too. Let's say that I take this V that I've got right here and I put that V, or the IR for the V, in here. Wouldn't that give me P equals I times R, or I squared R? Does everybody see that? P equals I times R, I squared R. So that's another one of our equations that we use for power. Now, what if instead of putting the V in there, I solved this for I equals V over R, and I put the I in for that, the V over R in for that. Wouldn't they give me V times V divided by R? Or P equals V squared, that's a square, over R? That's right. That's another equation that we have. We call those three, this, this. For high school students, we call those the power equation. You may have learned the power equations in high school like that. But in fact, there's really only one power equation, and that's this one right here. That's your power equation. This is Ohm's law. If we use Ohm's law to substitute in, we get these other two here, but you don't have to remember those. This is all you really have to remember right here. And you're going to remember that because that is what power is. Now, when we look at this and the fact that we already know what power's combination of primary units are, we also know that I is a primary unit, isn't it? I is current, I is amps. So I could solve for V. V is just power divided by I, right? So power, we know, is going to be a kilogram meter squared over seconds cubed, and we're going to divide that by current. Now, is that a kilogram meter squared per amp seconds cubed, or is that a kilogram meter squared amp per seconds cubed? Where does that amp go? Does that amp go into the denominator of the numerator or the numerator of the numerator? Well, it's just third grade all over again, isn't it? I know you were sitting in third grade and you were thinking, where is this complex fraction simplification going to help me in my life? Where is you teaching me complex fraction simplification going to help me in my life? Let's go through complex fraction simplification for a second, right? 6/9 divided by 3/7. What does that equal, right? 6/9 times 7/3, isn't it? So 6 times 7, that would be 42. And 9 times 3 is going to be 27. Well, of course it is. So yes, we can do the same thing here. We've got kilogram meters squared divided by seconds cubed times, and remember, that's amps over 1, right? So it'll be 1 over amps. So I've got a kilogram meter squared over seconds cubed amp. Kilogram, boy, that kilogram didn't come out too well, but you get the idea. Kilogram meters squared over seconds cubed amp. And we have a nickname for a kilogram meters squared over seconds cubed amp. It's called a volt, right? So normal people call it a volt. We don't. We call it a kilogram meter squared over seconds cubed amp. That's what we do. We're not done yet, because let's look at these other two things. P equals I squared R and P equals V squared over R. Well, look at this, P equals I squared R. Well, if P equals I squared R, then doesn't R equal P divided by I squared? So R equals P divided by I squared. Well, let's do that. We got the kilogram meters squared per seconds cubed, so we go kilogram meters squared per seconds cubed divided by amps squared. And I think everybody is getting that third grade complex fraction simplification down to a science now. And you all realize that that is a kilogram meters squared over seconds cubed amp squared. We do have a nickname for that. A kilogram meter squared over seconds cubed amp squared. I mean, who would want to say that constantly, right? Hey, could you hand me 1.2 kilogram meter squared per second? No, nobody says that. So we call it an ohm, right? So that's what we've got. Now I'm just going to take a peek at my thing here and see what, actually I seem to have a bit of time here. Yep. I've still got about four minutes left. I'm running out of paper though. I'm trying to decide what we could go on to. We really want to now go on to charge and to look at charge and to understand charge and to understand electron flow. And that's one thing that I really want to put down here too. No matter where we're going, we always want to remember that the charge on an electron is minus 1.602 times 10 to the minus 19 coulombs, right? That's the next thing we're going to talk about is we're going to talk about charge and we're going to talk about things. So as far as dimensions and units go, but this is something that we always want to remember. Also, as engineers, we always want to remember pi 3.14159. That's what you want to remember pi as. Now, I know you're thinking, can I remember 3.1416? No. My father's generation could remember it as 3.1416. We have to remember it as 3.14159. You know, Euler's constant, too. Euler's constant, everybody in electrical engineering should know that. Really everybody in any engineering, but more so in electrical engineering, Euler's constant is 2.71828. Remember it like that. And in fact, doesn't it just sort of roll off your tongue? 1828, right? 1415. It's just, you know, now that I've done that, you won't be able to forget it. You know, you'll try to forget it when you're going to sleep at night. I can't forget pi or Euler's constant. That's right. Don't forget those two. Those are very important constants in engineering. All right, well, I filled up that sheet, and I think I'm up at around 30 minutes now. So I'm going to hold it there. We're going to come back and we're going to do a third dimensions and units to try to cover things like capacitance, inductance, magnetic flux, magnetic intensity. And I want to cover those too because those are important as well for us. Now, you know, we haven't even covered pressure. And in engineering mechanics, of course, pressure is something that we want to look at too. So we really have another lecture on dimensions, and then we're going to start to get into really what we've been looking at here, the power equation, Ohm's law, all of those things. All right, I'll see you at the next lecture.